is electric charge? Or what I'll probably just call charge. All right, what do you know about electric charge?
There's positive, negative, and neutral.
Okay.
Charge.
So we seem to have three varieties there. All right, so there's a positive, negative, and neutral. What else do you know?
The negative and positive attract each other.
Anything else? What about positive and positive?
Did it repel each other?
Do they?
I would say yes. Yes? They do repel?
Say it like you mean it.
Oh, they repel each other.
Yeah, okay. We can sum it all, and negative and negative.
Repel each other.
They also repel.
Yeah, so the classic opposites attract like repels. What about positive and neutral?
Do they consume each other? Like, it turns positive?
Wait, say it
Well,
again?
If it's a positive going to a neutral, is it automatically positive?
Depends on,
Oh.
if I've got a positive charge and a neutral, some neutral object here,
Mhm.
It tracks it just a little bit.
so I thought neutral was called neutral because it doesn't attract or repel to charges.
Oh.
It's shown, right?
Yeah.
Okay.
Does it make like a dipole on the neutral, whatever it is?
Yeah, I noticed that you're using the right hand rule during part of that test, so I assume you've had some of this before. Yeah. So what happens to, whether neutral is attracted, repelled, or does nothing really, it depends. There are situations, as Sean mentioned, we can create a dipole, and so we'll talk about that a little bit later on. All right, so we have these things that are positive, negative, neutral. We know that the opposite charges attract, like repels. And then neutral is sort of a, it depends. Where do these charges exist?
Anywhere?
Oh, yeah, I was looking for something more specific, but, okay. Probably within our own personal experience, yes. I can make an argument for not anywhere.
And subatomic particles.
Okay, keep going.
I mean, electrons are negative.
Okay, so we'll start out. So we have these crazy things called electrons, assuming that they exist, which is the shorthand is just E with a negative sign there.
The protons are positive. Neutrons are neutral.
And so we have these three basic components right here. Protons, were they made up of anything? Or electrons? Are any of these individual particles, or are they made up of stuff? I'm just trying to find out what people know. That's. Ian, you look like you want to say something.
Technically, aren't they made of quarks?
Which ones?
Protons and neutrons.
Yeah. So these are made up of quarks. What about electrons?
I think they're just an individual particle.
As best as we know. There is a theory floating out there. We don't have the ability to actually test it, so it's just, theorists, as long as it's not unallowed, they're gonna pretend it's true, and Then later on, when we find out that it is true, they're hailed as geniuses for their foresight, but most of it is just complete garbage and never makes it anywhere. There is a theory out there that the electrons and quarks are made up of these things called prions, not the biological prions. So, whether that goes anywhere or not, I don't know. Possibly that it'll be in your children's textbooks or your grandchildren's textbooks. All right, but we still haven't gotten to the fundamental question of what is charge. And I'm gonna go ahead and spoil part of that, is that we don't really know. There seems to be this property of materials such that there are three types, of which two of them will repel, and then we got this other one over here that we can work into a theory. But we are going to pretend that this charge exists, and there is evidence to support this, that there is this fundamental property that has these characteristics. Also thrown into this idea of electrons. I'm still partway through a book called Electrons Don't Exist. And so do recognize that and there's evidence to support the theory, but it is a theory that these things exist, and we can do a great deal with this idea that these things exist. But it does get a little bit tricky at times, because electrons, we can picture as point particles a lot of the time, and other times treating them as point particles doesn't work. So, but for the most of this course, we will treat electrons as these point particles, and we will pretend that they exist, or we will assume that they exist. That's probably better than pretend. All right, so we have these subatomic particles. Let's just go at the electron, proton, neutron level. Where do those things exist? In general.
Inside atoms,
Okay, are they all sort of clumped together and mismatched?
the protons and neutrons are in the nucleus and the electrons are around the outside.
And again, another model that works really well for most of what we do, but at some point that does fall apart. But we will assume for now that the planetary orbit model is valid. So we got this nucleus here with protons and neutrons, and we can there are some aspects of physics where they're treated the same, in which case they're called nucleons. And then the electrons are out here somewhere. So how do I get an electron to move? Or what is one way to get an electron to move?
More electrons?
Say it again?
Wait, opposites attract, so protons to pull it?
How would that
I
work?
mean, actually, sorry, I didn't think through.
None of you have siblings? It's wintertime, almost wintertime. Gina, you look like you were trying to say something.
I'm trying to gather my thoughts on how to say it.
Okay. While she's gathering thoughts. Okay, I guess we will sort of leave that there. That you got closer to what you want to say?
Not really.
All right. So if I have an atom here with electrons, protons, and neutrons, what's going to be the simplest thing to rip away from the atom?
Electrons.
Yeah. And so there are a couple things to keep in mind as you go through the conceptual piece of this, is that 99.9% of the time, the charge that moves is the electron. Now we can get positive charges to move. I mean, it is possible. You need some equipment to do that. Or we can I can move protons quite easily, and you're about to see a demonstration here of by moving protons. It's going to be exciting. I'm going to move the protons in this table. There we go. Thank you very much. Typically, if you want to move a proton, you have to actually move the object itself. It doesn't strip the proton away. Unlike electrons, which we can easily strip away. If any of you shocked yourselves in wintertime putting gas into the car, that spark, those are electrons that are jumping from one object to another. They are not, as some students have tried to convince me, protons jumping from one object to another. If your protons jump from your hand to the car, that means you're taking a little bit of your skin off. I think that would hurt more. All right, so let's, I guess one other thing before we get into the demo. The symbol for charge is, as you would expect, a Q, naturally. I suspect that when they were first starting out, Q stands for quantity, or whatever the Latin is there, or a capital Q. Now, the typical convention is that little q here stands for, this is a single charge, and this is a collection of charges. And that's a typical convention in physics, is that, for instance, momentum is the letter P. It's a lowercase p if you're talking about the momentum of a single object. It's an uppercase P if you're talking about a collection of objects. I tend to use uppercase q and lowercase q almost interchangeably, but textbooks stick to that convention. There's some gray areas which give me an excuse to not stick to that all the time. There's nothing that I do where, I'm trying to trick you with a capital Q or a lowercase q. Just think of Q as the charge of something. All right, so these. Oh. The rods are all gone. I'm going to step away for a moment and see if I can find the PVC. So I basically want to get electrons either on here or off here. I want to charge this piece of PVC pipe. And we'll see if this works well enough. So how can I get electrons on it or off it? When you shock yourself putting gas into the car in wintertime, how do you build up the charge then? You're either positively charged and the electrons jump from the car to you, or you're negatively charged and the electrons jump from you to the car. But how does that imbalance show up?
Something to do with static electricity?
Something to do with
Rubbing
it.
your feet on the carpet?
Say it again?
Like rubbing your socks on the carpet and then touching the doorknob?
Absolutely. For cars, if you have cloth seats, that you're more apt to shock yourself. So I'm going to rub this. All right. Is it charged?
Yes.
I appreciate the faith. Let's find out. This is an electroscope. I guess you have the worst angle, Sarah. Can you see it?
Yes.
There are leaves in there. Now, I'm assuming that everyone's eyesight is much better than mine. I guess, Alicia, you're the farthest away. Can you see the leaves? There are these two metal leaves in there.
Mm-hmm.
All right. So if this is charged, what's going to happen when I bring it closer to here?
It'll swing one way or the other.
So both will swing this way or both swing that way?
I don't know.
I was trying to figure out, is that what you were saying?
That's what I thought, but I'm not sure.
That's okay. Take chances, make mistakes, get messy. Well, let's see what happens. There's some twitching going on there. So what are the leaves doing? It's just an observation, I'm not asking for any deep physics there. What did the leaves do when I brought this closer?
They moved.
How? I heard they moved.
Yeah.
Okay, how did they move?
They twitched.
It kinda like swung up.
Okay, so they seem to go away from each other.
Yeah.
Why?
They must have like charges if they're repelling.
Yeah, like charges.
Okay, so how do they have like charges? I didn't transfer any electrons or, now, if I rub rabbit fur or PVC, most likely this is negatively charged. There's no way for us to really tell what we have right here, but we'll just work with that for right now. This is negative, if this is negatively charged, how did those things suddenly have like charges? Because they're together right now.
All the electrons went into the leaves.
Why? Which, oh, you said all the electrons, what electrons?
From well, not all of them, but some of the electrons from the pipe to the leaves.
Odds are against that, that any of the electrons left the pipe. In theory, I could develop a large enough static charge that some would jump, but I don't think I did that. But you are right, the electrons did go into the leaves. The question is why?
You're neutral? Well, you said neutral.
Well, that's neutral right now,
Okay, okay.
or it should be. Well, let's see if it happens again. Probably have to charge this up again. I've done this in summertime. It works horribly in summertime. So another question is, why does it really work horribly in summertime?
It's less moisture, or less more moisture.
Yep. Especially in Columbia, South Carolina. Horrible. All right, so they moved apart, they move back together. They move apart, move back together. Why do they move apart when I bring it closer? Besides, the electrons go into the leaves.
There's charge going. There's some charge going into it.
There's some charge
Going into it, like they're making move.
going into what? Into the leaves or the whole thing? Not sure?
Not sure about that one.
All right, let's say that some electrons did jump from here into here. This is neutral to start with, and I have electrons jump into it. What would that say about the electroscope then? If I had electrons go from here to there?
It's negative.
Yes. So the whole thing would be negatively charged. The electrons hit each other, they would spread out. So the leaves would stay apart if the electrons jump from here to here. That's my evidence for why probably not many electrons jumped within it. But why, when I bring this closer, do the leaves separate a little bit?
They're sharing electrons. Like instead of transferring, they're just kind of sharing, and then when they go away, they go back to the.
No, just as a side tip, electron sharing is more of a chemistry thing.
So if it's like neutral all the way through, and then you bring electrons closer to it, do the electrons at the top want to get away from it
And where do they go?
to the bottom?
Yes. So because this is negatively charged, I bring a negatively charged object towards it, the electrons in the ball here will then scatter. Like the Romans invading southeast England, and then you have the tribes moving off into Scotland and Ireland, which is why they both speak Gaelic. Although different forms, I think. So this metal piece right here is a conductor. So electrons will move relatively easily through it. There's this piece right here, this is, I believe, bakelite, that is an insulator. So that the metal does not touch the metal casing here at all. And the glass is there to prevent a breeze from affecting it. So let me charge up. Let's see if this one works better. Charge it up again. I'm gonna bring it closer. The leaves should go out because these electrons are chasing those electrons away. And now I touch it. What's gonna happen when I take the rod away?
It's gonna go back to its original.
Okay, so we have speculation go back. Anyone else?
I'll say it stays the same just to be argumentative.
Okay, so we've got stays exactly like that and goes back to, I guess, the original. Anyone want to go for the middle? So we'll stick with those two. And take it away. It's somewhere in between. Why are they still staying apart?
Because you've transferred some of the charge by touching.
Yeah, all right. So now this whole thing is negatively charged. When I pull this away, the electrons that were in the leaves try to spread out again because they no longer have this threat coming from above. The electrons move throughout, which means some of the electrons in the leaves will come back up into the ball. So the repulsion in the leaves is not as strong as it was before because it didn't lose electrons in. Some of the electrons moved up to here. So how would I get the leaves to go back to normal? This is negatively charged. How do I stop that?
Touching it to the white void like you did before.
That would do it? Or just touch it myself? If you've heard of the term ground, I mean, it doesn't necessarily mean the actual ground, although that's where it comes from. But if you have some large object which can give up electrons if needed or take